So as usual, we have an intuitive sense of what a reflection does, right? We draw a fixed line and think of that line as being our mirror for our reflection. And then the reflection should be defined by the property that every point's image is just an equal distance on the opposite side of the mirror from its pre-image, right? If I stand 5 feet in front of a mirror, then my image is the same as me with opposite-handedness standing 5 feet on the other side of the mirror, right? Physicists call that a virtual image because it's not a real location. It's like through a mirror somehow, but still, that's how we understand how mirrors work. To actually set that down in linear algebra reality is exceedingly obnoxious to do. If my line of reflection has the equation y equals mx, so it passes through the origin and has a slope of m, then I need this nasty equation here to define the reflection of the point xy through the line y equals mx. It looks like a mess. We can still represent it with matrix multiplication if we're so inclined, and it gives us a little bit better tools for understanding how it works. But it's still not terrific. 1 minus m squared, 2m, 2m, m squared minus 1. And so we can talk about the linear algebraic properties of this transformation. For example, its trace is equal to 0. Its determinant is equal to, well, you'll have to compute the determinant yourself and see. I know the answer, but it's a good exercise to do. But it doesn't really give us that geometric understanding that we want. And as you know, if we had to do anything with the algebra in this formula, I don't know, I would pull my hair out, and I like algebra, so I don't know what that says. So in a coordinate-free sense, we'll define it using this figure as motivation. That if we want every point to be the same distance away from the mirror as its image is, then what that does is it sets up the mirror as the locus of points which is equidistant from both each point and its pre-image. But we have a theorem, 1.5.1, that tells us how to characterize the locus of points that are equidistant from 2 points. We call that the perpendicular bisector of the line segment joining those 2 points. And so that's how we'll define a reflection. A transformation is a reflection if there exists a fixed line, which I'm calling L in the definition, but is called K in this figure up here. If there exists a fixed line that has the property that for every point in the plane P, if I connect P with its image under this transformation, so maybe I'll call this now P instead of C. If I connect P and P prime with a segment, then what we need is we need the mirror to be the perpendicular bisector of that segment. So the congruence marks here stand, but then we also need a right angle to be right there. So because we know from the foundations of geometry how to define a perpendicular bisector, this gives us a way of defining what it means for a transformation to be a reflection using just those foundational tools and not coordinates. But it still remains for us to prove that a transformation defined in this way actually is an isometry. That if I have 2 points, say P and A or something back in my pre-image, that the distance between those 2 points in the pre-image always agrees with the distance between the images. So we still have to prove that each of the 3 types of transformations that we've seen today are in fact isometries. But then once we've done that, that gives us a lot of tools to work with. We'll eventually be able to answer the question about whether every isometry is related to these 3 examples. We'd like to say yes, but we have some work to do. But the first step is just to see that these 3 in fact qualify by themselves. So that's what we'll do